law of change of angular momentum. If we have a particle in space, so we can denote this particle with mass m like this, so this is a point, and it has some trajectory, and this trajectory has tangent, okay, and we know that velocity of the particle always belongs to tangent, so v is always in tangent. So v is a velocity of particle, and if we investigate the motion of the particles, so sure we need to measure the displacement, so we can use this displacement vector, so how far this particle from the origin of coordinate system, r is displacement vector. We can calculate the vector of momentum. It's a m by velocity, and it's vector 2, and it has the same vector properties as velocity, because the only difference of p in comparison is v is a different size, because we multiplied velocity by some number, scalar number, so it's 5, 10, so p is 10 times greater or 5 times greater if my mass is 10 or 5 respectively. So it keeps direction, and p is also in tangent but has different size if mass is not 1. So m is a mass of particle, and momentum p is m by v, mass by velocity. Okay, so we knew this. If we multiply this equation by displacement vector from the left side using vector multiplication, we get this equation. So we multiply left side, it is r by p is equal, and we multiply right side, it's r by this right side. And this is a new physical quantity we call angular momentum, and we use a letter L for this, and it is a vector. So we can write that angular momentum is equal to r by momentum. We can continue with calculation by making a derivative with respect to time, and we apply it to both sides of equation. So if we make a derivative of left side of equation, we get a derivative of L with respect to time. And if we continue to make a derivative of the right side of this equation, we must notice that this is a derivative of multiplication. So we must keep some rule about making a derivative of multiplication. So we use a derivative for the first term of multiplication, it is dr over dt by, and we rewrite this second term as it was here, plus, and we rewrite this term by, this is a vector multiplication sign, and we make a derivative of this term. So it is m, it is constant, it's out of derivative, and dv over dt. Okay, so this is a derivative of this equation. We can notice that derivative of velocity with respect to time is acceleration, and m by acceleration is force, is external force acting to this particle and changing the motion state. And here we can also notice that dr over dt is velocity. So we can rewrite this equation into this form. So it is dl over dt is equal m this m by velocity by velocity by vector multiplication, plus r from here by force. And we also know that r, displacement by force, is a moment. It is a moment of external forces. And we also know that if we make a vector multiplication of two collinear vectors, because this is v and this is v, okay, these vectors are collinear, and multiplication of two collinear vectors, if we use a vector multiplication, it is 0, and 0 multiplied by everything is again 0. So what remains here is this equation, dl over dt is m. So change of angular momentum in time is equal to moment of external forces. And this is a definition, important definition of this law. So it is a law of change of angular momentum in differential form, because there is differential of angular momentum. We can integrate this in differential equation and we get this. So if we use integration sign, so if we multiply both sides of equation by elementary time dt, so we get dl is equal m by dt, and we put here equation signs with limits. So if we make an integration from time 1 to time 2, so at time 1 was angular momentum at state 1, it was L1, and here was angular momentum in state 2, L2. So finally we get the law of change of angular momentum in integral form. So this is an impulse of moments, so this is em, so it is impulse of moment. Impulse of moment is equal to a difference of angular momentums, so L2 minus L1. We can continue. So this is law of change of angular momentum in integral form. We can continue. So this difference L2 minus L1 is equal R2 by, this is integral, this is vector sign multiplication. So, and this is Pm by V is momentum, minus there is angular momentum at state 2. And because m is not changing during the process, we assume that mass of the particle doesn't change during the motion. So we can put the mass out of the brackets and this remains. So it is m by r2 by vector sign v2 minus r1 v1. So now we can make some example to demonstrate the use of law of change of angular momentum. And we will make an example of mathematical pendulum. Again, we did it before, but we used a different method. We used a method of free body diagram, and now we use a method. We use this law of change of angular momentum. So let's draw three-dimensional coordinate system, and there is a rotational joint, there is a rope or string, massless string of length m, and there is a particle with mass m, and it makes motion in this plane. So it is a plane YZ, and x is perpendicular to this plane. So we will use this law of change of angular momentum, and because it is in fact rotation about one axis, it is one-dimensional case. So we can rewrite this vector equation to component form about x. So it is d of Lx component with respect to t is equal to force moment around x. So the trajectory of this particle is a part of circle, and velocity of this particle is always in tangent, and tangent is perpendicular to this string. So we know something about direction of velocity. There is a acting force, it's an external force, it's a gravity force acting to this particle. If we want to use this equation, first we need to start with accomplish the angular momentum. So angular momentum about x-axis is displacement vector, so it's a radius by velocity. This is a radius by velocity and by m, because this is p. This is p, and radius by p is angular momentum, where p is only momentum. What we know about velocity, if we use phi, this angle, for measuring the displacement, we can say it follows from a motion on the circular trajectory. So velocity, if particle travels on a circular trajectory, is radius by angular velocity. Angular velocity is usually denoted as omega, and it is derivative of angle with respect to time. So we can add that it is L as a radius by mass by L by angular velocity. This is velocity v. So we can continue. We can make a derivative of Lx with respect to time. Okay, so the only physical quantity needs to be derived is phi, because this is the only physical quantity changing in time. It is velocity. Okay, L is a radius, is constant, mass is a constant, so we can rewrite it. There is mass, there is L square, and there is a time derivative of phi with two dots. It is angular acceleration. Phi with two dots is another derivative of angular velocity, phi with dot. So it is d phi with dot over dt. Okay, it's angular acceleration. So we got the left side of this equation. This is the left side of that equation. And next we need to define a moment of external forces around x-axis. This is caused by the only external force, so there is a tangent component of g-force. There is angle phi again, so this component has a size g by sinus phi. So the moment of this force g by sinus phi about x-axis is g sinus phi by L. And finally we need to decide about direction, plus or minus. So it is motion around this axis. And if we use right hand rule, so if we make oriented the thumb in direction of plus x axis, the fingers of right hand shows a positive direction of rotation. So this is a positive direction of rotation, and we can notice that this force makes a different direction of rotation. So this is a negative moment, okay? It acts against positive direction. So there must be minus against plus direction. Okay, so we have right side of equation, and we can substitute to this equation star, or this is star with prime, okay, star with prime. So m by L square phi with two dots, what is a substitution of for derivative of angular momentum with respect to time, is equal moment of external forces, where g is m by g, so it is m by g by L by sinus phi. And we can cancel mass, we can cancel 1L, and we can divide it by L, because we want to rewrite this equation into standard form. Standard form of equation is when the highest derivative is standing alone, has no coefficient, so we divide it by L, and we get with phi with two dots plus g over L sinus phi is equal to 0, what is principal equation of motion of mathematical pendulum. We got this equation already in previous example when we solved mathematical pendulum using free body diagram method, and further calculation, subsequent calculation, how to get the angle with respect to time, this function, how to solve the motion of pendulum, is the same as in previous example.